Hello, good morning, everyone. Welcome to the second BLADES2BUILD Summer School in Athens. Um, as you know, we are the research lab of advanced composites and nanomaterials here in NTUA. Our lab is established now almost 20 years in NTUA, and our main pillars of activities are composites, polymers, and synthesis of nanomaterials, together with some other semi-pillars that we have that support the three main pillars of our lab. Our first group is the composites group that we are also involved, myself and Dionysis. Within the composite group, we do all of the parts of composites materials, from production of carbon fibers through continuous carbonization lines, the continuous lines of surface treatments of the fibers in order to size our fibers. The composites manufacturing, which is more of a lab scale process. The other two are in a pilot scale. And our pilot composites recycling line. Our polymer groups proceeds from the processing and recycling group. The filament production, the 3D filament productions that we use our own polymers that we either recycled or produced, and then the 3D printing. And for the nanomaterials groups, we synthesize a lot of nanomaterials. Most commonly, we synthesize carbon nanotubes in order to use them in sizing solutions, few layer graphenes, PCMs, subs, and other different nanomaterials that we can use either in construction, in composites, in coatings, or in energy sectors. We have two ways in synthesizing the nanomaterials. The one way is our pilot reactor, that we can produce either subs or PCMs, etc. And we have also our CVD, where we produce carbon nanotubes and few layer graphene. Then all of our materials are being characterized with different methods that we have in our lab. Either through mechanical testing, microscopes, chromatography, electrochemical analysis, conductivity measurements, and surface analysis. The target of this summer school is to focus on the end-of-life management and recycling of composites materials, especially carbon fiber reinforced polymers, and to address the challenges of the recyclability, the circularity, and sustainability in composite materials. We are going to see carbon fiber production, surface treatment, prepreg manufacturing, generally the properties of composite materials, nanomaterials, the end-of-life management, including recycling, and we will have the networking of the students. Now, for the first day, we will have some lectures regarding the recycling and the reuse of these materials, and lastly, we will have the lab activities. And tomorrow we will focus more on the carbon fiber production and the surface treatments, along with some sizing treatments and other perspectives on recycling of composite materials. And then again, we will have the lab activities. So our lecturers from our nanolab is myself, Dionysis, and as you know, most of you from the master program, Kate. And our invited lecturers is Natalia Lushnikova from TUE, and Shashank, again from TUE, and Mr. Soulis, he is from NTUA from a different department. So we start with Maria Kosarli. She will present Blades to Build, the project that is based on our summer school here.
Thank you, Maria, for the introduction. So welcome to the summer school and good morning from my side too. My name is Maria Kosarli. I am a senior R&D project manager in Global Consulting Sustainability. We are a company located in Norway, outside Oslo. And we are supporting this project in terms of dissemination and communication of the activities that are performing inside the project. So the concept of this project, let me start with some details, technical details of the project. So Blades to Build is a project funded by the European Commission under Horizon Europe programme. So the concept is to improve and support circularity options of end-of-life wind blades by exploring three different circular stages: direct reuse of the wind blade waste, repurpose of individual materials of the blades, and recycling the blade and the glass fiber textile scraps from the wind blade manufacturing in cement clinker co-processing as an alternative fuel. So more specifically, the ambition of this project, as we can see, is based in the 10 R's, as we are saying, in levels of recycling. So Blades to Build is targeting in R3 and R4, reuse and repair, and R7 and R8, recycle, and of course R9, recover energy, as we said, as an alternative fuel. So in this, let's say, arrow that we can see, the lowest environmental impact, reuse without repair, is in level 0, R0, and level 10 is the level considered most environmentally harmful and corresponds to landfilling. This is something that we want to avoid. So the project, the consortium of the project, the partners that are involved are four universities: the Technical University of Denmark, who is also the coordinator of the project, of course, National Technical University of Athens, the WTH Aachen University, and the Eindhoven University of Technology, from which we have also some invited speakers today in the summer school. So in terms of industrial partners, we can see, I think that for all of us, we can see some very famous names like Holcim, like Acciona Construction, PreZero, that is a recycling company, and they have a very crucial role in this project. We will see more. Elton Recycling, Renault Consulting, Endesa, LM Wind Power, and GE Renewable Energy. So this is the workflow of Blades to Build. We are starting from the characterization of the wind turbine blade waste and the developed methods on solvolysis. Another aspect is the development of circular building materials with the waste. And the main achievement of this project is the construction of a demonstration plant. Actually, it is a recycling factory that has been built by the project to recycle end-of-life wind turbine blades. And of course, in terms of industrial scale, also some activities have been performed for concrete in pavements and other applications. So today we will be very focused in this, the construction of the demonstration plant. We will see firstly, some results that are from Sasan. They will present it after, so I will not be inside the results, just saying that an aspect of this project is the recycling of polymer-based composites. And let's go to the Blades to Build demonstration plant. What is the target? This plant aims to enable the circularity of wind turbine blades by converting them into secondary raw materials, primarily intended for the construction industry. So very, very informally, this project takes the wind turbine scraps and we put them inside concrete or cement or generally construction materials. So the demonstration plant is located in Valladolid, Spain. It has the capacity to up to recycle 6,000 tons per year, and the construction started last June. And with the main equipment to be inside in December. And here is a plan of, or some parts of the plant. So the first one is the reception and weighting. So some wind turbine blades are cut into 5 or 6 meter sections. They arrive at the plant, they are stored at the outer area, and then we are starting with the pre-treatment. So they are transferred inside the plant. We have some sear with a hydraulic sear. We remove some metal components, and then we are starting with a mechanical recycle.
So, good morning, everyone. Firstly, I'll take this moment to thank both Blades to Build and NTUA for giving me this opportunity to be a part of this summer school. And also, special thanks to both Marias and Dionysus. Um, yeah, today I'll be talking about this particular topic of rethinking polymer composites and how we as researchers can think about recycling and the future of polymer composites. So this is actually the overview and objectives for the day. So I'll be talking right from polymer composites and at market size, and also later on I'll be talking about my own research, which is again part of Blades to Build. And later on I'll also give a small hint about future directions of this composite recycling. But Well, before diving deep into this lecture today, I also want to introduce myself. So, yeah, I'm Shashank Tumkukarnik. And also, thanks to the person who actually clicked this picture yesterday. Yeah, currently I'm working as a doctoral researcher at TU Eindhoven in the Netherlands. Um, and also, I have a master's degree in chemical and energy engineering from a German university called Otto von Guericke University. And also, I have a bachelor's degree in mechanical engineering from India. And also, as you can see here, these are my research expertise, and these are the topics which I'm currently working on. That is obviously polymer composites and recycling of fibrous materials. And yeah, also I work with different types of material characterization and life cycle assessment. And also, I'm also curious and exploring a bit of material informatics. So today, uh, I'll be talking mostly about this polymer composites. So before going deep into this concept of polymer composites, we also need to think, or we also need to learn more about the history of these polymer composites. So did you know that polymer composites was already been used back in 3400 BC? So people in Mesopotamia already had been using this material to construct their houses, walls, etc. And later on, in the mid in the early 1900s, we actually saw a great shift in this particular area of polymer composites when there was a chemical revolution which changed the entire scenario of composite materials. So in the early 1900s, there was a big market which started off with new synthetic resins which were developed. The first synthetic resin which was developed was called bakelite. So as we all know, this is actually the material which still is being used by us, but with a different name called PFA. And also in the early 1900s, there was also the invention of glass fiber, which took place by Owen and Connings, um, which again changed the entire scenario of polymer composite market. And later on in 1960s, when we started seeing carbon fibers in the market, there was a huge boom in aerospace applications, marine applications, and also automobile applications. And since we all know that composite materials are being used in all sorts of application recently, we also need to see what is actually the market size of these polymer composites. So, according to the survey, it says that between 2025 and 2035, the composite market will actually double uh, in size, and the approximate value would be around $152 billion. So just imagine how big the market is. And also among this, the, the GFRP or the glass reinforced composites are actually predominantly um, dominating the entire market of composite materials with around 67 or 68%, and the rest is actually dominated by CFRPs. And again, CFRP or the carbon reinforced composites is actually a new thing, um, which is having around $30 billion market. But with this growth potential in the composite industry, we also need to think about the waste material which is getting generated, right? So the expected waste generation by around 2030 for CFRP waste would be around 34,000 tons per year. However, we also need to think about the GFRP waste which is getting generated because, yeah, GFRPs were the first polymer composites which came into picture even before CFRPs. So the expected waste generation for these composites will be around 112,000 tons per year, which is literally a staggering number. And there are quite a few challenges when it comes to the end of life management of these materials. The first and foremost thing would be the non-biodegradable nature of this polymer composite, which actually makes it very challenging for both the researchers and industries to recycle such materials. And again, we also need to invest more energy into this particular recycling, which is again a huge challenge. And also seeing the industrial growth in the polymer composite area, we tend to see more um, waste material getting generated over the years. And also the important part of recycling of these polymer composites is the nature of the material itself. That is, most of the composite materials are made with thermoset resin just to have more strength compared to the thermoplastics. So this is also one of the challenges which has to be addressed in the coming days. And today I'll be focusing more on the wind industry because, yeah, today we'll be talking mostly about the Blades to Build project, which is mainly about the recycling of wind turbine blades. So let me give you a brief introduction about how wind industry is growing these days. So as we all know, in the recent years, climate change and global warming are being seriously considered by all the countries around the globe. Therefore, a successful shift to a climate neutral society is urgently needed to address this particular problem. So recently, according to Paris Agreement, Europe aims to reduce greenhouse gas emissions by around 55% compared to those of 1990s. And also, according to European Green Deal, an ambitious goal has been set to reduce greenhouse gas emissions to net zero by the year 2050. Considering all these goals to achieve deep decarbonization, uh, there is a huge market for renewable energy and 100% utilization of renewable energy in the coming years. And according to the stats, um, there is actually an upward trend in the utilization of renewable energy sources in the recent years, right from geothermal, biomass to solar, hydropower, and wind energy. And however, out of these renewable energy sources, wind power actually has been one of the most important sources of energy producers because of its environmentally friendly nature and multiple wind energy resources. And also in 2020, we see that wind power has actually accounted for almost 15% of the entire electricity generated. And now, as a wise man once said, with great power comes the great responsibility. On one hand, we should be happy that wind energy is growing rapidly, which helps us to achieve this net zero carbon emissions. However, on the other hand, it is equally problematic to see huge amount of waste generated in the form of old decommissioned wind turbine blades. So, as per Wind Europe reports, a total of around 350,000 tons of blade waste is predicted from the onshore wind industry by the year 2030. And as a matter of fact, there are lots of European countries such as Germany, Netherlands, Spain, Denmark, who are already working on this. And also, they're decommissioning a large number of turbines in the coming years, which has led to this particular problem, and which might eventually generate almost 9,000 tons per year. And it is expected to go around 520,000 tons by the year 2030. And amongst this, one of the good things is that almost 70 to 80% of the wind turbine materials are recyclable. For example, the generators and the support structure of the wind turbine farms or the wind turbine itself is recyclable. But the real problem actually lies with with these plates, which are almost non-recyclable because of the composition of the material. Because this particular material or this particular structure of a turbine blade is actually made of so-called composite materials. And to be specific, most of these blades are made up of either carbon fibers or glass fibers, which would have almost 60 to 70% of the reinforcement in it. And the rest would be the thermoset resin, which is one of the challenges which we need to focus on. And currently, there are quite a few popular strategies which are being used in the industry, such as landfill and incineration. So, you think these are good for the environment? All right. So yeah, also we as researchers are coming up with different strategies in order to address this particular problem of wind turbine blades, such as mechanical recycling, chemical recycling, and also thermal recycling. But yeah, today I'll be mainly focusing on mechanical recycling of these blade waste, and also my colleagues from NTUA will be talking mostly about chemical and thermal recycling. So therefore, to address this particular gap, European Union actually established a project called BLADES2BUILD, which aims to develop circular construction materials by predominantly applying mechanical recycling methods. And as already Maria um, said, this particular BLADES2BUILD project is actually aiming to achieve TRL 7 level. And this, again, this actually consists of many project partners around Europe, and we at DUE are actually aiming to develop circular construction materials such as cementitious materials and polymer composite materials. So today I'll be focusing mainly on polymer composites, and my colleague Natalia will be talking mostly about how these materials can be used in cementitious materials as well. And in the recent years, we have actually seen how um, glass fibers can be reprocessed and made into new secondary composites. And also, we have seen quite a few research which are actually making use of such wind turbine blade waste and different polymer composites, and yeah, they are able to produce different secondary composites. But my question is that can we really say or can we really consider such materials as recycled composites? Yeah, it's quite easy to put everything into a polymer matrix and call it a recycled composite, right? But here comes the actual question which we need to address: how to make them more circular. So how can we actually make such composite materials made out of recycled materials and make it more circular? So the answer would be the reprocessing of secondary composites. We need to address this particular question because it's, as I said, it's quite easy to put everything into a polymer matrix or any binder and call it a recycled composite. But we also need to think about the durability of these composites, or yeah, or the capacity of these materials, which can be used in different applications. But you might also be wondering why we need to actually think about reprocessing of these secondary composites when the cost of the virgin fiber itself is around 1 to 2 euros per kilo. But we also need to, as researchers, we also need to think about a few other parameters which are associated with these materials. For example, the embedded energy of these materials. For example, the wind turbine blade. The embodied energy of this would lie somewhere around 100 megajoules per kilogram, out of which the virgin glass fiber itself has around 13 to 30 megajoules per kilogram, and the rest would be for the polymer resin. So yeah, we need to actually think about this particular thing. And also we need to think about the energy consumption which is um, involved in such recycling strategies. For example, the energy consumed for mechanical recycling would be somewhere around zero point 0.1 to 4.8 megajoules per kilogram. So keeping all these in mind, we actually need to also think about certain challenges which we come across during this research. For example, there is a huge challenge with the material itself. As I said earlier, these composite materials are made up of glass fiber and thermoset resin. So when we start shredding these material, we end up having glass fibers with thermoset residue on it, which also is also quite a challenge to process these materials in secondary composites. And the second big challenge would be the interfacial strength. So let's say if we want to use these composites in certain applications which need to have a good amount of strength in it, then we also need to have a good interfacial strength between the fiber and the matrix, right? So this is one of the challenges which we need to also address. And also, since we are talking about recycled composites, we also need to think how good it is compared to virgin composites. And as I mentioned earlier, we are talking about the reprocessing of these secondary composites. So we need to also assess the performance of these composites when it is reprocessed for multiple cycles. So in my research, I've tried to address all these challenges, and yeah, I'll be presenting my results, which I've got in recent times. So, firstly, I would like to talk about materials itself. So, as I've already mentioned, this is actually the glass fiber which is coming out of wind turbine blade waste. As you can see here, the glass fiber has more thermoset residue on it, which actually becomes a huge problem while reprocessing it. So in my research, I've actually made use of a simple thermoplastic matrix, that is polypropylene, and also I have used a coupling agent called malic anhydride polypropylene to address the problem of interfacial adhesion. So also, as one of my colleagues actually asked this question about the um, size of the fibers. So here in this research, I've actually used around 20 millimeters, or let's say below 20 millimeters would be the size of these fibers. And this is actually a simple methodology which I've used to produce the secondary composites and reprocessing it. So at first we did some sieving of these materials, which we received it from Pre-Zero, one of our project partners, and we have used the coarse fraction of the wind turbine blade waste, which would have size fraction of somewhere around 5 millimeter, between 5 and 20 millimeters. And this would be actually fed into the extrusion, like twin screw extruder, and which, I mean, after the extrusion process, we get the pellets out of it, which will further be used in injection molding to produce all sort of specimens with different compositions. And later on, I've characterized these specimens for different to analyze different properties such as thermal properties, mechanical and flowability, whatnot. And later on, the same composites will be shredded again and fed into the extruder in order to reprocess these composites for two more reprocessing cycles. So after reprocessing the secondary composites and after producing these specimens from injection molding, we also analyzed structural properties of these composites. So as we all know, um, since these composites undergoes multiple reprocessing cycles, there is a possibility for these composites to lose its structural properties, right? So in order to assess these structural properties, we also did a FTIR in order to assess the effect of reprocessing on these properties. So as you can see here, the corresponding peaks for polypropylene was not altered, which means, yeah, the the polymer matrix was not entirely altered even after reprocessing them for 3 cycles. And similarly, the, the we were also able to see the peaks, which corresponds to ester linkage, which is already existing in the wind turbine blades. And also we are able to see the same peak, which corresponds to carbonyl bond, which is also for MAPP coupling agent. And also, we did not observe any alterations in the glass fiber peaks as well, which indicates that there was no significant structural change happening within the composite, and yeah, mostly the degradation which we can see would be thermo-oxidative degradation, but not sorry, it is actually not the thermo-oxidative degradation which is taking place, but it is rather thermomechanical. And after analyzing the structural properties, so After analyzing the structural properties, we also went through the assessment of thermal properties. So for example, the melting point for pure polypropylene would be around 162 degrees Celsius. However, with the addition of recycled materials, the melting point of composites were quietly increased to somewhere around 165 to 166 degrees Celsius. And also, due to the addition of these recycled materials from wind turbine blade waste, we can actually see a slight increase or a significant increase in the degradation temperature. So, yeah, I mean, the numbers itself say that the degradation temperature actually increased by around 5 to 12 degrees Celsius, which is actually a significant number. And also, we got to know that the melting point or the melting temperature of these composites were quite stable even at higher temperature ranges. And also, we were able to see a significant improvement in the crystallization temperature. And yeah, the, the, the crystallization temperature for recycled composites were quite good compared to the lower crystallization temperature, which we see usually in pure polypropylene and virgin composites. So the rate of crystallization happening in the recycled composites were quite good compared to the virgin composites. So as we can see here in the graph, we can literally see the big shift happening in the crystallization temperature compared to the virgin composites. And in order to understand this particular effect of crystallization, we also we kind of had a hypothesis where we thought there might be some sort of heterogeneous crystallization which is happening within the composite, where the fiber, both the fiber and the thermoset residue, is actually acting as nucleating agents, which propagates this crystallization process. And later on, in order to prove this particular hypothesis, we actually did this particular nucleation test using optical microscopy and hot disk, where we came to a conclusion that yes, indeed, the the fiber and the thermoset residue in the recycled material is actually acting are actually acting as nucleating agents, and which eventually helps the rate of crystallization. So as we can see here, pure polypropylene will crystallize somewhere around 127 degrees Celsius, and for fully in order to have in order to fully crystallize, this pure polypropylene would take somewhere around 780 seconds, so which is almost over 10 minutes. But again, in the case of virgin composites, so the rate of crystallization has actually come down to around 700 seconds, and also the crystallization temperature has also increased to 129 degrees Celsius, which obviously shows the effect of virgin fibers which are inside the polymer matrix, which helps the crystallization process. And coming to the recycled composites, both the fibers and the thermoset residue matrix actually helps the crystallization process even more compared to the virgin composites. So as you can see here, the time taken for in order to fully crystallize is somewhere around 600 Celsius, 600 seconds, which is almost 10 minutes, or let's say even 1 to 2 minutes below than that of pure polypropylene. So if at all, if you extrapolate this into an industrial level, this is obviously a significant number. And also, I would like to show this video. So as you can see here, the crystallization is happening rapidly, but if you can notice here at the beginning, yes. So you can clearly see the crystallization happening because of the thermoset residue and also um, the presence of glass fibers, which is actually enhancing the rate of crystallization. So yeah, it was understood that the rate of crystallization is mainly affected by the presence of both fibers and the matrix. And later on, yeah, obviously it was needed to understand the mechanical properties of these composites. So yeah, in order to have a better adhesion between the fiber and matrix, as I said, we also used a coupling agent called malic anhydride grafted polypropylene, which actually helped to enhance the adhesion between the fiber and the matrix. So as you can see here, this is actually the picture of the polypropylene composite before adding the MAPP coupling agent. So you can clearly see the difference where there is actually a poor addition between the fiber and the matrix. And later on, after using MAPP coupling agent, yes, it was indeed helpful in order to achieve the addition between the fiber and the matrix. So yeah, um, later on we also did some tensile testing and flexural testing. So as expected, in the first cycle, we got some lower tensile properties and flexural properties for recycled composites compared to virgin composites. And the recycled composites with coupling agent was able to achieve somewhere around 86% of the tensile strength compared to virgin composites. But later on, once we started reprocessing these composites, there was a significant rise in both tensile and flexural properties of recycled composites compared to the virgin ones. So in the third cycle, the recycled composites were able to achieve, or I can say they were able to retain somewhere around 98% of the strength compared to the virgin composites, which is obviously significant number in terms of strength enhancement. So there are quite a few reasons behind such an increase in the tensile and flexural properties of these materials. So one of those reasons would be the processing parameters, such as lower screw speed or lower melt temperature, which will also affect the tensile and flexural properties of these materials. But we also have certain other possible reasons which will affect the enhancement of these properties. The one would be the breakage of fiber agglomerates and thermoset residue. So as you have already seen, the material which will have thermoset residue on it, and also there is a tendency of these fibers getting agglomerated, which will also affect which will also affect the mechanical properties of these materials. So while we start reprocessing these materials, there is a tendency for these agglomerates to break into um, clean fibers, I would say. And also, since we are using the temperature zone somewhere around 180 to 200 degrees Celsius, even there is a slight possibility of thermoset residue um, getting degraded, which will obviously create a smooth surface, which will help the coupling agent to enhance the adhesion between the fiber and matrix. So yeah, in this case, I would say reprocessing actually helps um, the composites to enhance their mechanical properties and to give better performance. And moving ahead, we also need to think about the rheological properties which needs to be addressed because yeah, we are not developing such materials just for lab scale, right? We also need to have these materials which can be upscaled on an industrial level. So for such a thing to happen, we also need to have good rheological properties for these materials. So as you can see here, the melt flow rate of these composites were progressively increasing yeah, over the number of cycles. So as you can see here, the recycled composites had better melt flow rate compared to the virgin ones. Um, the one main reason for such thing to happen is that the higher the fiber loading is, the lower would be the melt flow rate because the fiber itself acts as it acts as barriers which will hinder the chain mobility of the polymer matrix. And also, the increase in melt flow rate for recycled composites can be attributed to the thermoset residue that might actually hinder the entanglement of polypropylene chains and thereby decrease the viscosity of the polypropylene. And also, we can see that there was an increasing trend for recycled composites with coupling agent. But there are also quite a few reasons behind this. One is that, yeah, obviously after the reprocessing, the molecular weight of polypropylene would eventually decrease, um, which enhance the melt flow rate of the composites. And also, there is a possibility of beta session reactions happening in polymer chains, which actually cut off the chains to like cut the long chains of polypropylene into a shorter chains, which will eventually increase the melt flow rate. And also, there is another possibility where due to the addition of coupling agent and few other things, even there might be a plasticizing effect, which will actually increase the melt flow rate of these composites. So since the recycled composites have better flowability, we can say that these composites are also favorable for injection molding. And yeah, there is a possible chance for these composites to be upscaled into an industrial level. And and also, um, it is always better to understand the life cycle assessment of these composites, right? Because yeah, we are talking about recycled materials, and again, we need to have some sort of um, yeah, we need to have some sort of positive effects of these recycled composites over virgin composites um, before saying yes, recycled composites are good for the market. No, sometimes even the recycled materials which we use might be producing higher carbon emissions compared to the virgin ones. So in order to assess these things, we also did an LCA assessment. So here we have actually shown the contribution analysis of these composites. So as you can see here, so the higher carbon emission was actually seen mostly in virgin composites. Yeah, which is obvious because we are making use of virgin polypropylene and virgin glass fibers, which will definitely have higher carbon emissions um, compared to the glass fibers coming out of wind turbine blades. So here, the carbon emission coming out of Pure polypropylene and virgin glass fiber would be somewhere around 69%. And the rest 31% of carbon emission is actually coming out of electricity. So yeah, you must be wondering, right? How can electricity actually give rise to higher carbon emissions? Yes, there is actually, um, I mean, we need to also think about the electricity we are getting from. For example, in 2025, Dutch electricity was produced from renewable sources, which was the highest contributor. So it was somewhere around 49%. But the rest, 48%, was from fossil resources, which is um, from coal burning and few other fossil resources. And the rest, 1 or 2%, would be from again from clean energy sources such as nuclear reactors. But compared to I mean, if at all, if we compare Dutch electricity with French electricity, there is a huge amount of electricity in France getting generated from clean energy sources. For example, the number would go as high as 88%. So yeah, if at all, if we are considering LCA analysis, we also need to think about the electricity which we are getting, because yeah, eventually this would give rise to a higher cost of recycled composites. And moving on, we also need to think how these recycled composites would actually benefit both environmentally and economically. So as I already have explained, these recycled composites have a good amount of environmental benefits, but we also need to think about the economical benefits, right? So, for example, when it comes to environmental benefits, yeah, we are considering recycling of these wind turbine blades over landfill and incineration, which is again a good point. And yeah, by making use of these recycled wind blades, we are reducing non-biodegradable waste, which actually goes into the nature. Um, yeah, I mean, also we can, um, yeah, we can actually cut off the virgin material resources. Instead, we can start making use of these recycled materials. And coming to the economical benefits, there is a huge potential for these recycled materials um, to have higher economical benefits compared to the virgin ones, because if at all, if we start making use of recycled carbon fibers, there is a tendency to reduce the cost of materials by around 70%. And also, if at all, if I need to include energy costs, there is a significant change in the energy costs when we start making use of recycled materials. So, for example, if we start making use of recycled carbon fibers, there is a huge decrease of somewhere around 98% in the energy costs. So, just to put that in perspective, the energy saved from using 1 ton of recycled carbon fiber instead of virgin fibers will actually, which is almost equivalent to the annual electricity consumption of around 40 homes. Just imagine the number. So if at all, if you scale these numbers to millions of tons of recycled materials, you are talking about energy equivalent to power a small nation like Greece, for example. And also, there is a huge market potential for these recycled materials. As we can see here, I mean, the growth potential is somewhere around 234 million to 700 millions by the year 2033, which is almost 200% increase, which is again a staggering number. And this would, uh, uh, meanwhile, the recycling industry will also create more jobs and or eventually reduce the cost of the materials which we make use of in our daily lives. But in order to implement all these things, we also need to think about future directions, right? So the first would be to design materials for which are suitable for recycling. So as engineers and researchers, we need to start thinking about developing materials which can have an inherent property of recycling in it. So yeah, we need to always think about the end of life management during initial design. For example, we need to think about what materials are compatible, how can we minimize contamination when we start thinking of recycling, and how can we actually simplify disassembly, etc. But when we start thinking about the materials, we also need to start making use of thermoplastic composites going forward, because yeah, there is as you all know, there is actually a recent trend um, where people have started making use of these thermoplastic composites even for higher strength applications. So, for example, even wind industries have actually started using thermoplastic composites to build wind turbine blades. So, for example, there is a thermoplastic resin which you might be knowing called helium resin, which wind industries have started using it, which will also give equivalent strength compared to thermoset resins. Again, when we start making use of thermoplastics, it is always easy to recycle it using extrusion or injection molding. And the next would be to optimize the entire process. So yeah, we have good amount of knowledge about these recycling techniques, and we obviously know that these technologies actually work. But now the challenge would be to improve the efficiency of these technologies, and also we need to think about how we can reduce the environmental footprint of these materials. So yeah, process optimization is completely data driven. So as we all know, there is a huge boom for AI these days. So yeah, we need to make use of such technologies to optimize the entire process, which helps the recycling industries to scale up. And the next would be to have a better industrial scale up. So as we all know, aeronautical and automobile industries have um, have already started implementing or scaling up this entire recycling processes, but there is still a gap in wind industries where we are not able to scale up the entire process into an industrial level. So yeah, we can start addressing this particular gap in the future or in the coming years. And last but not the least, yeah, we are all talking about circular economy integration. So we need to think how we can actually implement this particular circular economy um, in recycling perspective. So yeah, for that, again, we need good capital investment in order to integrate all these parameters. And also we need to have um, um, also we need to have a proper bonding between research and industries and governments, which can actually implement these policy frameworks, which will incentivize recycling processes. So I can say that the road ahead is challenging but achievable. Just that we as researchers, industries, we all need to come together in order to make this recycling a huge success. And finally, I would like to so yeah, finally, um, I would like to request you all to think circular, because yeah, it's quite easy for all of us to say, okay, we can recycle these materials, we can recycle those materials. Yeah, it's quite easy to just say these words, but we always need to um, inculcate these into our lives, for example, because yeah, as we all know, we have a disposable lifestyle where we just take, make, and dispose. But yeah, we need to start implementing these into our own lives so that we can start thinking circular. And yeah, we can make this a huge success. Once, once again, thank you all for your attention.
Thank you, thank you. And I have two questions regarding your, tensile strength mechanical decrease. The first one is, did you look at the void content before the virgin composites and after that the recyclable composites? And the second one, did you look at the fiber distributions? Thank you.
Yes, thanks for your question. Yes, we actually, I think if I understand it correctly, your first question was about the porosity of the material itself, right? So yeah, just to make it more make it more clear, the process which I've used is extrusion and injection molding. So in theory, it is um, will have less pores or less voids in the material itself when we are using these two processes. Because if, let's say, if at all, if I had used compression molding, for example, definitely, as you said, there might be a possibility to have more pores in it. But yeah, we have already done this analysis on porosity, and yeah, we have o- o- yeah, I can say we have less than 2% of it. And sorry, the next question was about? Yes, 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 yes. Since again, I would like to reiterate this particular thing that since we have used the injection molding and the flow direction would be really restricted, which makes the fibers to align itself in a proper direction, and we have good orientation in both recycled composites and virgin composites. But again, as I said, when we start reprocessing these composites, the fiber dispersion will be better in recycled composites. And since we have also used fibers with somewhere around 20 millimeters size, the even the length reduction is quite low in recycled composites.
Thank you very much for your presentation. I would like to ask, what type of challenges have you faced during the extrusion process? Because you're actually trying to distribute a thermoset material in a powder form in a thermoplastic one. So
Yeah, I
could you
mean,
please?
I
Yeah.
would say there was a huge challenge because, yeah, as you know, we need to start feeding the material into the extruders. which was a quite challenging process altogether because the material which we get from wind turbine blade waste is heterogeneous. So it might contain all sort of impurities in it, and also the fibers um, are agglomerated, which eventually makes the feeding a challenging task. So at times we also manually fed the materials into the extruder by just pushing it with a small metallic rod or something. Yeah, this is one of the challenges. But going forward, we might also need to think about having a better feeder systems for extrusion process where we can I mean we also have vibratory feeders, but it I mean, in my opinion, it doesn't actually cater the problem because, yeah, as I said, the material has too many agglomerations, which cannot be decreased just by having some sort of vibration in it. So, yeah, we need to also think about having a new system for it.
Very nice, thank you. We feel really close to this situation with our experiments.
Okay, nice to know that.
Uh, I'd like to ask a question to Shashank too. Do you think that the poor adhesion between the matrix and the recycled fibers are because of the remaining resin that appear in the mechanical recycled fibers?
Yes, indeed, yes. It is one of the possibilities because, as you know, the virgin fibers will have a smooth surface, which will improve the adhesion between the fiber and matrix. But since we have the thermoset residue on the fibers itself, it's quite challenging to have this adhesion. But um, also, the research says that the thermoset residue, since it has a higher surface roughness, it also helps um, helps in enhancing the adhesion. But the only thing is we need to make use of some sort of coupling agent. So if at all, if we start using a coupling agent, then the addition will actually improve a lot.
And have you compared them to the other fibers like chemical or thermal that do not
No,
have
not yet.
the?
I actually am working on it.
Okay,
Yeah.
okay,
Yeah, we have already discussed this.
okay. Perfect. Thank you.
Indeed, I'm also part of the group of building materials in Technical University of Eindhoven. And I'm a postdoctoral researcher and daily supervisor for two PhD candidates, Shashank and another PhD, Jeren Dualkulak. Unfortunately, she could not join us in person because now currently she is in Fukuoka in Japan to present part of this work basically at the conference on recycling waste. So we have like I tell it like it's kind of insight from our group. We have a concrete and mortar cement mortar ladies group, and we have quite unique situation with Shashank because we are not really our group mostly worked on mineral based materials, not much with polymers. I don't know about your background, so we will introduce each other and you will tell us more later, I guess, after before lunch. And I'm curious also about your experience. So probably mostly related to polymers. But today now I will talk a bit more about other materials, mineral-based materials, and how we can make use of this waste of wind turbine blades in circular design of concrete, because concrete is most globally like highly consumed building materials in the most of the countries. So my topic is wind turbine blade waste in concrete, replacement and reinforcement concrete for circular design. There were many questions about mechanical shredding, about the size, about the heterogeneous heterogeneity of the waste themselves. So I will try to address that also in my presentation. So our content, I'll try to be more precise on that, not repeat what Shashank already said. So we will talk about the physical characterization, chemical characterization of the waste and morphology. What was more important, I will focus on the properties which were more important for concrete, like to make use of this waste, basically a valuable resource for concrete. Function of this wind turbine blade waste in composite materials, how we try to combine different approaches on replacement, some valuable components like partial replacement of cement and aggregate, and make use of from this waste for reinforcement. And properties where we went in two directions, in two different materials. First one, it was normal weight concrete, and we tried to use the waste as they are. You will see the images, pictures, so they are really heterogeneous. And go to another direction, a bit different, to make use of that in lightweight aggregate. Now we applied for patent in Netherlands and EU, so I will not dive too much in details, but you will see the key outcomes of this research. So basically what you see here, this is our heterogeneous waste. You saw some pictures already. That's how we get them from our industrial partner, PreZero. You saw the plant, yeah? So these preliminary samples were used, were made by shredding of the waste, because shredding is I would say the simplest way to mechanically recycle this waste. For cutting, for crushing, it's more difficult to do that. So we receive the waste like from zero and until the 20, 60, 80 millimeters. So it was not sieve on the lowest part, but like from zero, but the highest was limited. And we sieved it, like it's also challenging to sieve to get the size of this waste because they're heterogeneous, as you see. And we make use of it, as I said, in concrete. You will see some test in detail. So this is a semio test when we make a notch to test flexural strength and to see how cracks propagated, because to make it cracks in a specific place in this beam. And lightweight aggregate. So you see lightweight aggregate, which totally looks really nice, aesthetical, but still it make up to 70%, from 70, 90%, it consists of wind turbine blade waste. So why wind turbine blade waste? I will not dive deeper in this. This is just wind turbine. Shashank mentioned the how many decommissioned wind turbine blades here with in the world globally, in Europe and United States. Here is the basically the paper from 2017. So probably this forecast already changed, and probably to higher level. So this is wind turbine blade waste up to 2050, and you see how it increases year by year. So our motivation was, yes, indeed, we have and the essence of the project, we have wind turbine blade waste. There are a lot of them, and we have many already wind turbines with blades which are end their service life, because the service life ended 20-25 years. Our summer school mostly devoted of carbon fiber enforced polymers, which are more recent generations of wind turbine blades, but we dealt with glass fiber reinforced polymers, from wind turbine blades, and it's like, cheaper material, and it's really difficult to recycle. We'll have 2 megatons of these wind turbine blades in more than 20 years. So the end of life is really challenging for waste stream of wind turbine blades. It's difficult to recycle, that was mentioned several times. And we try to make use of it in concrete. Because we can get highest consumption of this waste in this material because of this highest volume. So the key concept here in this direction was use wind turbine blade waste as a potential resource for concrete and make it multifunctional. So, okay, we have heterogeneous waste, you saw it. So it's a problem, it's headache to even to sieve them, to sort them. So we decided why we try to make use from this waste as it is. So the goal was to maximize waste content safely for concrete quality and human health. So preliminary we had tests, I don't include it, but our industrial partners tested health and safety risks. So we basically use this mechanically shredded, non-selective wind turbine blade waste. Here is the process of shredding of wind turbine. So they've preliminary cut it into pieces, then shredded. And basically, like visualization, what we see in optical microscopy analysis, and we try to visualize it. So we have powder, actually like 40 to 45% is basically powder. Then we have a kind of fibers, and we have a kind of flakes, which are really flat, but particles, which, spoiler, are not really efficient. The less efficient part of this waste is these flakes. And if we go to chemical composition, we can compare the chemical composition of cement, the key material for concrete, and chemical composition of wind turbine blade waste. So since we have loss in ignition like 31%, so around 31, 32%, we have this polymer component, and the rest is was glass fiber. So the density of this material itself is around 1.8 gram per cubic centimeter. Water absorption was around 23 centimeters, and we had epoxy based composite and inorganic components, mostly glass fiber, 68%. So what we see in optical microscopy, and you see this variety and this imperfect particles with some powder grains, which more has some polymers. We had some mix of microfibers and powder. We have a fiber, like basically glass fiber, which is glued together with polymer. We have flaws and irregularities on fiber cross section basically after shredding and damage. So we tried to, when we use new materials in cement-based composites or other composites, we try to replace more valuable components, as we understand. So like here we visualize how we try to replace in classical concrete. So here is the figure A. You see the concrete with fine aggregate, coarse aggregate, and cement matrix. And we try, this is the total volume of concrete. We choose this a portion of selected replacement. And we replace it with shredded wind turbine blades waste. And C, basically, we also, like, we have concrete with this incorporated wind turbine blades waste. So we try to replace some particles and try to reforms. So we try to combine two effects on concrete with this waste, since we have fibrous particles, since we have powder, and since we have flakes. So this is particle size distribution of all the components we used. We used traditional natural sand, like rather fine sand, traditional coarse aggregate, gravel, so all common traditional materials for Netherlands. We used SEM1, and we used the most important here is, since we have many components, the most important is the calculation of mixed design. So here in our group, in building materials group TUE, we use a lot particle packing approach. And here we use it also much to make material like concrete more dense, because the density of wind turbine blade waste is significantly lower than other components like cement and aggregates. First, second, as you see, and I repeated it several times, the waste is really heterogeneous. So we also have challenges because for applying this particle packing approach, because it's really not granular material. Yeah. So for fibers, for flakes, it was challenging, but still we managed to optimize the known model, Andresen and Andersen, is modified model, to this target curve. So we used different mix designs. We had control mix designs. We have concrete with 1% of wind turbine blade waste, 3% and 5% by total mass of the concrete. And here you can see our like amount of this waste in these 4 different types of concrete. Here is like we recalculated what is the percentage of fiber reinforcement. So it was from 0 to 2.6 by volume, and amount per component, how much aggregate we replaced. So we replaced up to 10%, 10.2% of aggregate with this waste, and I repeat waste, but it's resource, alternative resource, I would say, and cement replacement up to 4.4%. Here is the process of mixing, because we mixed dry components. We tried different approaches to, it's also challenging to make the process homogeneous, like the mixture homogeneous. So we initially added cement and sand, then we added wind turbine blade waste to mix them with finer components, then we add coarse aggregate, and then we added water and superplasticity. So the higher was percentage of wind turbine blade waste, the higher was the duration of mixing, because it was challenging to make it more or less homogeneous. So here are the properties of concrete. This is basically what we see. We try to get concrete with slump class S3. So this is a kind of like medium workability. But even when we use quite a lot of superplasticity, we could not make it for higher dosage of wind turbine blade waste, because we see like the waste make a kind of like framework, and it doesn't let the mixture flow. And here you can see that the superplasticity content goes up, this blue line, but the slump goes down, unfortunately. And here is, you can see the values of this fresh concrete. We have some like air content, which significantly was low, because we use this packing, optimal packing approach for this material. And for hardened concrete, we tested compressive strengths at 7 and 28 days and correlated with cement paste. So here is the red line. This is cement paste for the same dosage of wind turbine blade waste. And green bars, this is 7 days compressive strength, and 28 days, they're blue bars. So you can see that in compression, what is relevant to cement, paste, and concrete, we have significant, not high, but still some decrease in compressive strength. For split in tensile strength, since we have this effect of like bridging cracks and some reinforcement effect, we see increasing of strength, especially at early age, 7 days. This is green line. And at 28 days, we have some decreasing, but for dosage, 5% dosage of wind turbine blade waste, due to its reinforcement effect, we have quite nice results comparable to control sample. And here is a test fracture of the concrete samples at 28 days split in test in our structural engineering lab. So you can see this crack in the middle. For other properties, because we try to describe the deformation, fracture, elastic modulus of the material, as well as durability aspects. So here is a elastic modulus result of concrete specimens, so they mostly a bit slyer for higher dosage of wind turbine blade waste, but for 1% and 3%, it's comparable to control one, but it's not below than 30 gigapascals. And for relationship in terms of relationship with replacement, aggregate replacement, and elastic modulus, we understand that elastic modulus reduces and the aggregate replacement increases. So basically, we have like lower stiffness and more porous nature of wind turbine blade waste leads to these consequences. And here is the results of a fracture, like testing of fracture behavior, flexural strength. This is figure A. So we can see that at higher dosage, the flexural strength actually the tendency repeats the split in tensile strength. We have really nice results and insignificant reduction at the lower percentage of waste. And at 5%, we have the same comparing to control waste. Figure B shows load CMOD curves for concrete beams with notch. I showed you the previous picture, and fracture toughness increases. Figure C, but figure D, the fracture energy reduces a bit because the density is a bit lower. So it's like overlapping effects, opposite effects for this wind turbine blades waste. But in mostly we observe that increasing of wind turbine blade waste enhances ductility and bridges cracks. And what we can see at curves of that basically the despite reduced stiffness, we have increasing residual flexural strength. This is the green lines for dosage 5% at graph B. So it's like 2.5 times higher than for control sample. And here basically is a setup for testing SIMUD test and at figure C, and for figure B, you can see the setup for testing elastic modulus. So we did it in our partners lab. For the properties of like drying shrinkage, we also measured, and we also addressed the expansion during alkali silica reaction because we have glass fiber coated with polymer, but still. So the results show that we still have higher significantly lower drying shrinkage than required for concrete, and silica reactivity actually is really comparatively low comparative to standards. So it's below 0.1% supposed to be. So we have below 0.02 expansion. And for microstructure, you can see the concrete with like some images with concrete with maximum dosage of wind turbine blade waste. Here we can see some epoxy particles, we can see the matrix, we can see this transition zone. We can see some fibers, glass fibers and cement particles. So indeed, it's really heterogeneous materials. And inside of like larger particles, they used to like as serve as aggregate emplacement. So fibrous particles, they serve as reinforcement. So all these details are more described in our paper, which was recently published. This is a QR code when you can find this paper and get familiar with details, because while we were preparing to summer school, we received the confirmation that the paper was published in Construction and Building Materials Journal. So this is our concept in general. We used wide particle range of this waste. It's from 0.06 to 80 millimeters basically, but the core of this waste is up 20 millimeters we use. And we use optimized mix design. So under these terms, we can get compressive strengths to 45 MPa, slight reduction in stiffness, improved ductility and toughness, and increasing of residual flexural strengths. No alkali silica reaction risk observed, low shrinkage, and we can replace 10% of aggregate, around 4% of cement. And what next? So we saw that we are limited when we just put this waste as it is into the concrete. Otherwise, we need to redesign concrete mix, and we go beyond this optimal packing approach still, and we need to use quite a lot of superplasticizer, which also like expensive material. So what next? So we decided that we go to totally different material. Some like great discoveries start with by accident. So we found out that we have pelletizer in our lab. We have so much equipment that sometimes we don't know what. I mean, we like find something which is 20 years old. Let's say, oh, what's that? So we decided that, yeah, we can go, we have pelletizer, we can go and try to make pellets of this waste. It was not typical solution, and not so many, like we couldn't find many references on fibrous materials used for pelletizing, especially waste, but still we try to do it. So we have this heterogeneous mix, powder, fiber, flakes. So poor dispersion, high water demand, workability loss, reduced stiffness and stress. So risk of clustering when we are mixing, and limits of high volume application. This is the main source. But we have a kind of request from our industrial partners of the project, okay, how we can make use of this waste as much as possible in concrete or other materials. So we shifted the concept. I say we, but mostly Jeren. Sorry, I expropriate her results. But we mixed concrete all together. There were 3 ladies who mixed 300 liters of concrete in 3 days. So we did it, all these tests. So we moved to other conception. Instead of mixing waste, let's redesign material. So we convert these shredded wind turbine blades into pellets, lightweight aggregate, with control. So we can control here more. We can control size, shape. We basically sieve the waste to get at least to control the highest particle size. We have core shell structure because we use cement in small amount, and we have uniform, stable aggregate behavior. So no like unexpected things. So this is particle size distribution of raw materials we used. We used wind turbine blades waste of fine size, because we see, you saw at previous images, that we have a lot of powder and small fibers, like almost 40% of this, like regardless which upper size of the waste is. So we had 3 sizes of waste, up to 180 microns, comparable to cement, up to 2 millimeters, and up to 4 millimeters. And we have some one, like which hardening, rapid hardening. And we use the disc type pelletizer. We visualize it like to make it nicer, and forces acting on individual pellets. So Duran tried many, like we cannot vary much parameters for pelletizer, which we can vary speed, and we can vary angle of this pelletizer. And what we get is this visualization of, I will show you pictures of the pellets depending what type of waste we use. So it's a bigger fibers particles, so we have more this fiber inside. And this is schematic illustration when we have micro-sized particles, when we have more powder. So it's more like relevant to what we usually see in pellets. And here basically what we have, if we use this fibrous granular bigger size waste, and another part when we have more powder, yeah, so they look nicer. But this is also nice with fiber. So basically what we have here, this is our particle size distribution of different aggregates we had. We had 12 different mix designs, but after first trials, some of pellets were weak, so we went to 9 different mix designs. So we basically can replace fine and coarse aggregate from smallest to highest. This is a particle size in microns, up to 15 millimeters, and average crushing strength of produced aggregates. So the darker is the LE days 3 days up to 28 days. So here you can see the dosage of cement. Definitely we had 10, 20, and 30% of cement. The higher was the dosage of cement, the higher was crushing strength of these pellets, which is there's no surprise in it. And this is the density of pellets. Here is the parent density, specific density of the pellet, and bulk density. So you can see that, yeah, it's more or less the same, but the strength, regardless of the size of waste we used and dosage of cement, but you see the strength is different. And water absorption, it's also like in total porosity, water absorption was different. So the more dense, the more powder we have. So the less was water absorption, because the more dense was structure. And we also tested dry and shrinkage mortar. So this higher value was for mortar with sand. So basically we, sorry, not with sand, like 100 replacement of aggregate with pellets, shrinkage increased significantly, but for lower load dosage it was quite okay. And for alkali silica reaction expansion, this highest value at 15 days, it was basically for sand-based mortar. And for pellets with finer particles and fibers, it was quite significantly lower values. So basically, this is a summary what we get of lightweight properties. So we have quite like high porosity from 50 to 85% with internal voids. We have a kind of encapsulation of this waste and covered with cement. We had like thermal conductivity. I didn't include this data, but thermal conductivity quite low, so it's a good also can be good insulation. It has stable microstructure due to this protective shell. So we can enable like here high volume recycling of this wind turbine blade waste, reduce density of concrete mortar, and improve thermal insulation properties. So here are the key conclusions for both of these materials. We definitely can use both of these technologies, and yeah, we're in contact with our industrial partners. They already have some trials with pellets as well, and you saw already in presentation of Maria Cosarli that the trials of concrete were basically batched and molded in by our industrial partners for even higher dosage of waste. So we work on that, and it's also can be one of the options for large volume recycling of wind turbine blade waste and turning this waste into valuable resources. We will be happy to answer your questions now or later. Here is our emails, me and Duran. So thank you for your attention. And if you have questions, please.
Sorry, I would like to discuss about the cost of this material. Let's say this additive. Is that comparable to let's say cement?
The cost, you mean? It definitely depends. Shashank mentioned LCA and cost. Like it definitely depends since it's waste. So the cost will depend. Like it doesn't cost much itself. So we need to calculate based on the how this plant will go, because definitely the laboratory cost will be more expensive, several times expensive than industrial one. But the main like environmental impact and cost can be caused by transporting. So we need to use this waste as close like to the place of generation. So that's why you saw when we like recycle that in wind farm. So this is one of the options. Compared to cement, it's several times lower, but now unfortunately I'm not ready to say the numbers of the cost.
Okay, thank you for the presentation and the nice information. I've got a few questions, if you don't mind.
Yeah, sure.
On slide 2, you mentioned about like you are using the materials for replacing different aspects of the material. So like cement, sand, and aggregate.
Yes.
And using like the original materials the one has received, right?
Yes. Second, it was, I guess,
yeah,
just
that material. So that it's like, yeah, the picture. Go back, if you go back.
This
yeah,
one,
that one.
yes.
Yeah, that
Yes,
one.
the
So
form, yep.
these materials, in terms of like processing, when you said about replacing the aggregate, like fine and coarse aggregate, what type of what aspect did you consider for the application? Sizes?
For now, we considered the size. So we did not like the size of flake, yeah, or like the length of the fiber for reinforcement. If it's like more or less like powder material, so we consider it's like finer. So we replace cement with comparable size, like bigger, so we can replace the fine aggregate. So definitely, like we cannot say that we replace, for instance, coarse aggregate like as equal replacement. I would say all the research, as you can see, if we replace just granular material with this flake, we definitely get significant reduction in strength. So we try to, like, with optimal packing method, we try to minimize this negative effect of the waste, basically.
Okay. So you see the yellow parts, these ones in that mix. How did you get these ones?
Which one do you mean?
Yeah, you see the picture in the middle?
Yeah.
You've got like the flakes, you've got the powder, and there is
Yeah.
the yellow part. What is that, the yellow part? What is that part of the material? Is it part of the waste?
It's a part, it's as we received it, it's basically glass fiber reinforced plastic from wind turbine blades after shredding. So mostly it's like 2 stages shredding. So we just received it as it is from like 0 till like 20 millimeters, till 40 millimeters, till 60 millimeters. So we just make like images and try to find out what is the particle size distribution. For powder, we used yeah, we try to sieve separately powders, and we also grind materials. We have some other research on cement paste, but this we just look at this with all possible methods we have: optical microscopies, SEM, and just sieving, make images, and then to calculate from different batches what is the average percentage of each component. What is a powder? What is the like fiber flakes? And combine the terminology from different resources, how we can call these materials. But the key idea, since it's really difficult to separate these waste, and also even, okay, when like, yeah, these flakes are rotating, yeah, in sieving, and you still have some big fibers, or on these flakes, you still have accumulation, like because of this electrostatical effect, you see the accumulation of dust on them. So we try to make use of what we have. So we basically could not have impact on this composition. We just make use of what we get from our industrial partners, from PreZero, from Spain. Yeah.
You talked about the alkali environment that proceeds from the cement mixtures. How do you tackle the degradation that this alkali environment may have on the glass fibers?
Yeah, so we make this standard method from like American Standard Materials Institute for like measuring the expansion of the after 14 days of testing. So I suspect if we just make glass fiber, like virgin glass fiber, use it, so we will have significant effect. But since here we have, first of all, not very high dosage of waste. Second, it's still mostly glass fiber is coated with polymer, so it basically protects it from this reaction with alkaline cement environment. By the way, we also, it was not a part of this, but also we had some preliminary tests on other like non-alkaline materials like gypsum. It's not really like common, but it also can be used because, yeah, gypsum has a neutral environment, so we don't have these problems. So here we didn't observe these problems, but I know that our colleagues made the test on like virgin glass fiber, and it's all like fiber which has less contaminants with epoxy, so they observed some alkali silica reaction. If there's also not a like cement environment, but like direct alkaline environment, some aggressive environment.
Have you thought about using in the future carbon fibers, recycled carbon fibers within the?
Yeah, thank you for this question. It's a good question, and I was thinking about this before our summer school first topic, it's a good question. The thing is that I can see really potential of carbon fiber using like thermal chemical recycling for getting carbon fiber, since it's more like expensive material, it's thermal version. But for glass fiber, the key challenge that it's not a like expensive material itself. So it's challenging also to use it for concrete, since it's high volume mostly. So we need some high volume material, and if it's waste, it's supposed to be material which is really easy to get. So mechanical shredding for that, it's a good, for now it's a good option. But I would see that for probably for motors, it would be interesting to work with carbon fiber reinforced plastic for some specific applications, for instance. So probably we will get more, more insights on that. But for some other, not for like high volume concrete, but for mortars, I think it will be also nice to compare.
Thank you.
Thank you. Yeah, sure.
Just last slide when Susan said about think circular. From your perspective, I know this is maybe something you've not been considered yet, but the recycling of the concrete, that including that waste.
Yes, it's the
What
most
would be-
popular question we get all the time.
What would be the
Yeah.
potentials for that?
Thank you. Mostly we get it. So I was surprised that we don't have it, but you asked it. Thank you. Yeah. So this is also we are thinking about this now. So we had this question from our industrial partners like Holcim. So for now, we think that we need to use the same procedures as we can do with any fiber reinforced concrete. So for now, we can only, let's say, downcycle this waste, if we mean concrete waste. So it can be like crushed, shredded, and used as a, like, for instance, aggregate. So because it's, but we're already working on that as well. Thank you.
And Dr. Kate Drobeta will present regarding the thermal recycling of composite materials through pyrolysis.
Thank you very much for your introduction, and thank you for joining Blades to Build workshop. Actually, this presentation will be sharing the fundamentals of composite recycling, not only from pyrolysis, but will be a shared presentation with Maria, also for solvolysis, because these are the two main processes that are taking place within Blades to Build process. But since this workshop is a training workshop, you need to understand the main fundamentals of the recycling of composite materials. And this will also be the stepping stone for our next interactive session, where you'll be also involved, and you will also have the opportunity to brainstorm and share your ideas and knowledge. So to start with some initial things about composites. Here you may see the resin types that are mainly used for CFRPs, for carbon fiber reinforced polymers. This is a pyramid which shows which are the most important and commercially used polymers. These polymers are also combined with carbon fibers that can be found in different types. We are talking about short carbon fibers in an entangled form or in a powdered form. These are randomly oriented fibers. On unidirectional composites, which means that we have either longitudinal, orthotropic, or quasi-isotropic fabrics, and on the bidirectional fabrics that could be with different weaves. The three of the top of the pyramid polymers, epoxy, vinyl ester, and polyester, are also very common in GFRPs, so in the glass fiber reinforced polymers. These can be combined again with different type of glass fibers, again either on specific weaves or on randomly oriented fabrics. So thermosets are polymers with high molecular weight, as you know, offering alternative properties and applications compared to the thermoplastics. Their cross-linked molecular structure offers mechanical strength, thermal stability, endurance, and chemical resistance. However, this cross-linked nature is what makes the recycling challenging. The 3D network prevents the material from melting, reforming, or dissolving under heat. Consequently, processing causes severe fiber degradation and limits the economical viability of recovering the high-value reinforcement. So there are some technical and economic barriers that make difficult the recycling, and that's why we have invented different recycling technologies that will be presented in the next in order to overcome these barriers that are related to the irreversible cross-linking, to energy-intensive degradation of the matrix, to the fiber damage and reduced strength that occurs after the recycling, the contamination and sorting issues that were also discussed previously, and the low economic viability of the current methodologies. That's why we would like to have novel techniques that will enable to have more efficient recycling processes. Also, there are several chemical degradation byproducts where we have not found yet how we can use them and exploit them. So due to these barriers, several techniques for recycling have been developed. Here you may see actually a wheel that includes categorization of chemical recycling procedures, thermal recycling, and mechanical recycling. In thermal recycling, which will be the first part of this presentation, we have the pyrolysis and oxidation, fluidized bed reactors, and also microwave-assisted technologies. The mechanical recycling is what you have already seen before in the previous presentations. We actually shred down the material, excuse me, yeah. So we shred down the material and we are trying to downscale it and reuse it in other applications. About chemical recycling, we have again several techniques. Maria will talk about them afterwards. And there are also several hybrid techniques, as you may see in the next. So the first part is mainly focused on the pyrolysis and fluidized bed. In pyrolysis, we have a chemical decomposition for chemicals. We have also a recovery of the fillers and the fibers. In fluidized bed, we retain also the fibers and fillers, but also we could have energy recovery. And there is also a combustion where we have the main energy recovery, but it's not very eco-friendly and very efficient. Here you may see that there are also hybrid technologies, hybrid composite recycling methods. For example, we could have some chemical, electrochemical techniques. We could also have a combination of the techniques in a series and sequential manner. And generally, we are trying to have recycling of different composites, end-of-life composite coming from different industries. Aerospace, from the energy sector, as for example, BLADES2BUILD project before showed to you, automobile, marine, sporting goods, medical sector, and also from sanitary field. The point is that each recycling technology can apply in a specific composite due to the special characteristic of the composite itself. Either this is the fiber reinforcement or if this is the resin type. So this means that the end use of the recovered product, and this was actually a question before from one of the colleagues, can go either again back to the composite industry, either on the construction industry, as we have seen before in BLADES2BUILD presentation, or to be used as value-added fuels. So we have different routes, different cycles, either in closed-loop recycling or in open-loop recycling. So to focus on the two main thermal processes, there are the pyrolysis and fluidized bed. The main principle of pyrolysis is the thermal degradation of the cross-linked polymer matrix in an oxygen-free, in an inert atmosphere. And in fluidized bed, we have a rapid high-temperature stream or hot air to vaporize the polymer resin matrix of the composite material, liberating and recovering the underlying reinforcing fibers. For example, it could be carbon fiber or glass fiber for its reuse. Here you may see some indicative reactors. For the pyrolysis, actually we are using heat, pressure, and the scrap, which is the feedstock. the FRP scrap, and this enables the material separation on the recovered fibers, on the recovered fillers, or on the oils that are produced. A fluidized bed reactor is, as you may see here, a more complicated apparatus. It's actually a system including the fluidized bed, which is filled with sand. This is the filling material. There is a feedstock with the shredded CFRP waste. We use also a fan in order to feed the reactor with the hot air. And most of the cases, there is a cyclone which separates the material coming from the top of the reactor. Also, we could have an exhaust oxidation and heat recovery system, both from the inlet and outlet. So here we are talking about a fully integrated chemical reactor system. In the first case, the pyrolysis reactor is something more simple. Actually, we are talking about a furnace. The advantages of pyrolysis is that there is a unique ability to transform organic waste into valuable products, for example, the bio-oil, biochar, or synthetic gas. And very important is that we are able to reclaim whole patches, as you may see here in the picture, from a publication that has been done from our colleagues in the lab. The fluidized bed has advantages such as the high quality fiber recovery, the contaminant tolerance, that we could have energy recovery, continuous operations since we are talking about an integrated system, economic viability, and low carbon footprint. However, there are some disadvantages, as for example, the significant mechanical property degradation of the recovered fibers, the high operational energy costs, that we get mainly short and fluffy fiber length and not a whole patch, and sometimes that there are high greenhouse gas emissions. Also, the pyrolysis has some drawbacks. It's not the optimum process, since the pyrolysis plants require significant upfront capital investment, which means that due to the high temperature and oxygen-free reactors that are needed, we need sophisticated control systems, which are expensive to build and install, and this is when we are talking about an installation in industry. The operating costs are also substantial because the process is energy intensive, requiring a constant supply of heat to maintain the high temperatures and ongoing maintenance, which is very critical for the safety and efficiency. The synthetic gas can also offset some energy needs, but the process often requires a net energy input, especially during its startup. So actually, these are the main issues that sometimes we need to handle if we want to have a energy efficient process, and also to find a way to use the secondary refining, actually the refining products, which are used as a fuel sometimes, but there is a lot of refining needed and upscaling if we want to have a second use of the oils produced during the pyrolysis. That's why in Suspense project, we try to have a sustainable pyrolysis conceptualization. Suspense project deals for the structural sandwiches and hollow composite parts from automotive, boat, and aerospace markets. And we have designed here in NTUA, in our laboratory, a new system that could combine the carbonization of carbon fibers production with the pyrolysis. So here we are trying actually to blend, to combine two energy intensive processes. The first one is the carbon fiber production that consists from different steps, as for example, the melt spinning, the stabilization, the carbonization, and the surface treatment. And from all these steps, we take the carbonization, which is a procedure that goes up to 1,800 degrees, and trying to recover the hot gases, or generally the heat produced from this process, and to deliver them to pyrolysis by designing a new pilot line, a new system that could use the heat from the carbonization for the pyrolysis, which takes place to 500 up to 600 degrees. By this, we have a closed loop. Actually, we are combining both the production of the carbon fibers with the reclamation of carbon fibers. So in parallel, we have production and recycling. So this was the design of the pilot line that we have here in NTUA. We had already a carbonization furnace working in batch as a batch process. So we have redesigned the inlet and outlet system. We have actually manufactured a connection between the two systems, which is the carbonization furnace and the pyrolysis. And we have also tried to optimize the energy needed for both. Here you may see some of the modifications and designs that have been carried out by our team in collaboration with the Mechanical Engineering School. And we have concluded that the optimum way to retrieve, actually to recover this heat, is to use the heat generated from the carbonization furnace, which is exposed. Some parts of the furnace is exposed, actually. And there we have designed a coil that could cover and wind, as you may see here in the image, the exposed part of the furnace and deliver the heat through an inert gas that is inserted in this coil to the pyrolysis chamber that we have also designed. So here are some images from the current system as it is right now. And here it's also the pyrolysis chamber, which has been designed in order to be able to recover, to recycle actually CFRPs of 30 by 30 centimeters, to host 3 panels in its volume, and also to be used for chopped fibers that can be pyrolyzed or whole objects. And this has been also used in BLADES2BUILD project in order to deliver recycled chopped fibers to other partners for their manufacturing in the construction sector. Also, there is a capability to collect the pyrolysis oils for further valorization, as you may see in the lab visit that we will have at the end of the day. So you may see the whole pilot line, how this has been installed right now. And here are some real experiments on carbon fiber reinforced polymers. This is actually the protocol that have been developed by our colleagues in the lab and specifically from Stefania Termine, where we have the epoxy CFRPs that are first treated in nitrogen atmosphere at 550 degrees for 5 hours. This is in a lab scale, actually, apparatus. And then a post-pyrolysis treatment for 1 hour at 5 degrees in atmosphere, in air. By this, as you may see, we are able to separate the layers of composite, the different patches that consist the CFRP specimen, and they are really glossy and clean, as you may see from the pictures, which means that we have a very nice recovery of fibers without destroying them. So these were samples made from epoxy resin. Here are some chemical structures that you see that the epoxy resin consists of different parts, the part A and the part B. We are talking about actually bisphenol A as the main part A ingredient, and curing agents that could be amines or isocyanates. In general, the epoxy is a compound containing glycidyl ether functionality, characterized by the presence of the active epoxy or oxyrane ring. This is the important functional group of the epoxy resin, which is capable of undergoing the cross-linking process when initiated by base reagents, as mentioned before, the amine or also thiol groups. So what happens when we have an epoxy resin inside the pyrolysis furnace? We have two main stages, the cleavage stage and the polycondensation. There are several reactions that take place, radicals, intermediates that are produced, and the main breakage results to, for example, carbon monoxide, water, hydrogen, and also we have as a byproduct char, liquid, and the gas emissions. We have carbon dioxide formation, formaldehyde formation, and also water. So these are emissions that need to be measured on these experiments to have also the mass balance and to know what type of emissions occur from these type of processes. Similarly, glass fiber reinforced polymers can be pyrolyzed. In this case, and in our experiments, we had shredded epoxy GFRPs. So it was not the whole part, but shredded parts. Again, here the reaction took place at 550 degrees Celsius for 5 hours under nitrogen. And then again, a post-pyrolysis in order to remove the char that is deposited on the fibers at 500 degrees for 1 hour in air. So this methodology can also recover both chopped fibers and whole parts. The glass fiber reinforced polymers, as mentioned before, consist of polyester resin, which means that during the decomposition, we have the primary monomer of PET, which is terephthalic acid, benzoic acid, styrene, toluene, phenol, and acetone, as well as acetaldehyde, which is a common thermal breakdown product, and also non-condensable gases that are revealed to the atmosphere, like carbon dioxide, carbon monoxide, methane, hydrogen, and some light hydrocarbons, which all means that these processes are not very eco-friendly in terms of the emissions that they occur. So our studies and research need to focus on the reduction of the emissions that are produced during these processes, and actually to find new ways for also the recovery of the byproducts. So to conclude with this part, we have fibers that can be recovered through this methodology, and this can be applied on different sectors. For example, on automotive, aeronautics, energy, marine, for biomedical also applications, for industrial applications and machinery, and also on sport leisure products and electrical and electronic applications. So we are coming from very light applications, which are the leisure or commodity applications, going to non-critical structural applications, and concluding to very important structural applications or semi-structural applications. There are much more to consider about this, but let's go to the next part where my colleague Maria will talk about the solvolysis, so the chemical recycle options. So Maria, the floor is yours. Thank you.
Maybe someone has a question. Okay. So if someone has a question about paralysis, keep it for themselves at the end. So my name is Maria, as I told before, and I will present the chemical recycling of these composite materials through solvolysis. A small introduction. We all know that composite materials are now used almost everywhere in aerospace, automotive, wind energy, and construction. And generally, the global production of the composite materials right now exceeds more than 12 millions of tons annually. And most of them are thermosets composites that are more difficult to recycle. So what happens when they come to the end of their life and they need to be recycled or dismissed? So the problem with the composite materials is that their waste exceeds the 2 million tons annually, and most of them come from wind turbine blades and aircraft, and less than 20 of those composites are recycled now, right now. Up to 40 of these composites recycled waste are actually produced during the initial manufacturing of the composite materials. And the US and Europe by 2050 will have more than almost 1 million tons in waste just from aviation and wind turbine blades. The vast majority are now being landfilled or incinerated. And this is something that we are trying to move forward since, for example, Spain has forbidden landfilling this year, and they are now trying to move forward in other forms of recycling. So our goal is to recover the fibers in their optimal state in order to use them in new composite materials. as Kate said, we have three types of recycling: the thermal, the chemical, and the mechanical. And now we're going to talk about the chemical recycling that is divided in two methods: the low pressure chemical recycling that are mostly with acids and sometimes with alkaline environments, and then the supercritical solvolysis. So the mechanism of solvolysis with the epoxy resin, we have to see how the epoxy is produced. So as Kate said, epoxies are conducted through ether bonds. So the recycling comes through a transetherification through a nucleophilic substitution. And then the polyester resin, it says already in the name, is we have ester bonds. So we have a transesterification mechanism through again a nucleophilic substitution. So we have in both epoxy and polyester are nucleophilic centers that are being attacked in the solvolysis through our electrophilic either solvent or catalyst. So to compare these two processes, the low temperature and the high temperature solvolysis, the pros of the low temperature is that we have more mild conditions. That's why it's a low. It says already in the name. We need a lower energy demand and a more simpler equipment. The downside to this solvolysis is that it often requires catalysts or acids or alkaline environments, longer reaction times, and then the solvent recovery is more difficult. And the lastly and most importantly is that it does not dissolve the resin correctly, and it might give an incomplete result for our fiber reclamation. And now the near and supercritical conditions are obviously faster and more efficient. The solvent penetrates more efficiently within the matrix, and we have a more clean fiber recovery. However, the cost of the equipment is very high because we need a very specific and very costly equipment to do supercritical solvolysis. The pressure and the temperature are very high, so that means that we have a safety issue here that we have to tackle. And then the scaling up is more complex compared to the low temperatures. But in our case here, in our lab, we have tested both of them. And because of our applications, we consider that supercritical solvolysis is a better option for us since we have more clean fibers and less time. In the low temperature solvolysis, as you can see here, it was very easy to upscale from 100 milliliters to 10 liters reactors because the kinetics don't change dramatically when you upscale the reaction. However, as you can see, we had some fibers that were not cleaned properly, and we had to use more catalyst and then in order to clean the fibers. And then when we used more catalyst, we had problems with our fibers because the catalyst not only penetrated the resins but also degraded the fibers due to the alkali environment that we used. And now for the supercritical solvolysis, first we need to talk about what are supercritical fluids. So supercritical fluids are fluids that they're above their critical point. The critical point, it's a unique point for each liquid that can be reached in a specific pressure and temperature. And when a liquid reaches that form is neither a liquid or a gas. It has both of their, we can see both states. And these are more environmentally friendlier solvent because usually we use water and acetone or alcohols. The supercritical point of water is at 370, around 375 degrees and 220 bars, which is actually really high. However, the acetone is at 235 degrees and almost 50 bars. So acetone reaches the critical point quicker than water. In order to have a supercritical solvolysis, we need a very expensive, as I said, equipment. Here we can see a high pressure, high temperature reactor that can withstand up to 350 bars. The first reactor is a 100 milliliter reactor, and then the next one is a 4-liter reactor. What we have seen is that when we test and calculate the kinetics in the small reactor, they don't we don't have the same result in the big reactors. So in our big reactor, the kinetics change. So that's why the upscaling is different and it's more difficult because we don't have the same energy demands and the same time and the same temperatures and pressures needed in the small reactor to have the same results. However, we can see here that the difference between the fibers that the results through the supercritical solvolysis are very obvious because we have much cleaner fibers and fibers that are not degraded as much as in the low temperature solvolysis. Some future goals is to evaluate these fibers mechanically in order to see their potential in applications, to explore the liquid byproducts that we have within in our reaction, because the resin becomes a liquid byproduct that we can obtain and we can use as a carbon precursor to create new nanomaterials, to synthesize new nanomaterials. To assess this process through life cycle assessment and life cycle costs, so we can see if it's worth to recycle the fiber through solvolysis compared to mechanical recycling. And then, as we know, the solvolysis does not only attack the resin, but it also attacks the sizing of the fibers. So we need to resize the fibers to improve their surface treatments in order to reuse them in new applications. So maybe now is the time for questions for the pyrolysis and the solvolysis. Whoever wants to have a question.
Thank you. I don't know if I got it right, but is it possible through pyrolysis, is it possible to get back all the layers from a carbon item separately?
Yeah, and actually, the girl behind you has did it. Yeah, Stefania.
Okay.
Yes, so that's why we had a picture before with a real experiment that took place in our laboratory where the fiber patches were intact. So this is the advantage mainly of this procedure. I think that here it is. So on the right, on the bottom right part, you can see one by one, each of them is a separate layer that all of them were stacked to form the first piece that you can see on the top left.
Okay, thank you.
Stefania, would you like to comment on this, on the methodology you have followed? Yeah, better with the microphone, with the cube.
Thank you. So the main concept is to identify the parameters you want to apply in order to separate all the fibers, because this process is really dependent on the volume that the specimen has. For example, if you have a few layers, then it's more easy to reclaim each one of them. But if you have more thickness, then the decomposition of the resin gets trapped in the layers, so it becomes more challenging to separate. So you either have to increase the duration, or you have to increase the temperature or the inert gas. So you have to remove more of the volatiles that have been produced during the process. So it really depends on what are the specimens that you have, and adapt the parameters of your process. Welcome.
Thank you. Yes?
Thank you so much for your presentation. I just have two questions out of curiosity. One is about the length of the fibers itself. So as we all know that the length is actually a critical part um, when we are using such recycled fibers in all sort of applications. So what is the maximum fiber length which we can achieve through pyrolysis or solvolysis? And is it really dependent on the process itself, or is it really dependent on the material which we get at the first stage?
I will start with the pyrolysis. So in the furnace that we have designed, the chamber actually that we have designed, here, that is it, we are able to recover patches 30 by 30 centimeters, because this is the internal chamber. So this means that we have a composite, a plate, which is 30 by 30 with the fabrics which are 0.90 degrees. We can reclaim the full length. In other cases, we can chop down, as you have did in your work, and to have just short fibers, and this depends on the shredding machine that we are using. But our research was actually focused on recovering a full length in full parts and not to shred down the material. This was done for the purposes of blades to build, but in general, we're trying to recover the whole fabric or the full length if we are talking for unidirectional composites. But our limitation right now is the 30 by 30 chamber.
So it mainly depends on the size of the reactor.
On the size of the reactor and also on the way that the composite has been produced. Okay. Yeah, but for solvolysis, it's a different case. So Maria, you can say your limitation.
So again, the logic is that we have to see the volume of the reactor. So in the reactor of solvolysis, we have to be very cautious with the volume since we have these high pressures. So I think the longest that we have recycled was 5 centimeters. The goal is to try and recycle even longer fibers, but it doesn't always come to the reactor. Sometimes it comes to, for example, in BLADES2BUILD specimens, they were already shredded and given to us. So we couldn't choose the size of the specimens. So whatever size we receive as waste, those are the size that we have to deal with. The longer ones are the ones that we made in the lab so we can test and see our limitations. So at least now that's the longest that we have been.
Perfect. Also, one more question related to the operation costs, which you had already mentioned. So yeah, I mean, if let's say if new startups wants to invest money into this, so what sort of costs they need to think about. Like you also had mentioned that the heating system actually takes a lot of money into this. So
A chamber like this costs up to 25,000 euros. Your reactor costs 680, yeah, I think 60 was the small one, 80,000 euros, and small for an industry. So actually, I guess that for the solvolysis, the high pressure reactors are more expensive than the furnaces used for pyrolysis. And imagine that the furnaces used for pyrolysis do not go at very high temperatures. So in general, there are low-cost equipment in comparison with your case. There's also the energy needed to operate both systems. That's why we had invented this combined process with the carbonization of carbon fibers production. And what we are suggesting actually to industry is that the producers of carbon fibers to find a new market, which is the recycling, and to do both to produce and recycle. So by this, they could have energy savings. In your case, I think it's more difficult.
I think, I mean, solvolysis, as I said, the expensive part is the equipment because the solvent can be water. Water is, at least in Greece, it's almost free. But the thing is that compared to pyrolysis, we are operating at a lower temperature. So we are operating at 350 degrees compared to pyrolysis that is 550 degrees. As we have seen in glass fibers, at least, not carbon fibers, when we go above 350 degrees, we have a fiber degradation due to the temperature. So this is like a pro in the side of solvolysis, that we use lower temperatures, but we cannot compete with the costs compared to the pyrolysis.
So
it depends on your application. If you need the fibers to be applied in a high demand, mechanically demanding application, then you should go for solvolysis. If you don't mind the mechanical degradation of the fibers, then you can go to the pyrolysis option.